back to chapter 4. So last week we looked at how we can use Fourier series to solve problems where you have a periodic forcing function that's not a sinusoid, okay? And so we covered the theory behind finding Fourier series. We looked at odd and even functions, and we even did an example down here of one of these sorts of problems and how that relates to vibrating systems. And I talked about a procedure that you have to go through to solve for these sort of problems. Okay? You have to find the Fourier series, f of t, of that forcing function. Okay? And for every term in that forcing function, so you generally if there's a constant term, there'll be a constant term, and then there'll be a number of terms that are wrapped up in that sum command, okay, that sum sign. There'll be a number of terms, and what you need to do is you need to solve x for each of those problems, okay. Often there'll be a sinusoid involved in that because of the way that Fourier series is. And then once you've got those solutions for x of n, you then basically add them all up to get the total solution. Okay, so that's the problem, and that's a process that you have to go through to solve for them. Now, what I'm going to do is I'm going to do this problem. So it's a mass spring system, there's no damping, let's not worry about that, but instead of the forcing function on this slide, I'm going to do the forcing function that is in question 4 of your exercises. Okay? Now, so let's move to the visualizer. So, Fourier series example. So what we're going to do is we're going to find the Fourier series to the question, and then we're going to solve to find the response in terms of displacement based on this being the forcing function. Okay, so it's question 4 just says obtain the Fourier series of the function. We're going to take that one step further by, once we've got that Fourier series, we're going to then find the solution to a mass spring damper, a mass spring system if this was the forcing function. Okay. So the Fourier series that's been given, f of t as a function of time is basically t squared between -1, t and +1. Okay. And it repeats after every 2 seconds. So f of t plus 2 equals f of t. And if you were to draw it, it looks like the picture in the book. Basically, it's a series of parabolas. Okay, this is -1, this is +1, +1. This obviously would be 3. This would be -3. Okay, so the first step 1, we have to find the Fourier series for this function. Now we know the equation for Fourier series. We've got f of t is going to be a0 divided by 2 plus the sum from n equals 1 to infinity of an cosine n pi t over big T. This is the equation that's in your notes on page top of page 59. Plus Bn sine of, sorry, there's a 2 in here, 2n pi t upon t. Okay, that's the Fourier series. The equation for Fourier series for a general period. There is a 2 in that bracket at the top. Okay, that if you're having it unsure. But like I said, it's equation at top of page 59 in your notes. But because of the shape of the function, we can make some assumptions about an and bn, can't we? Is the function odd or even? It's even. So what does that mean? Sorry? There's only cos terms. So bn, we know, because it's an even function, all bn are 0. There's no sine terms in this problem. So all we've got is a cos term. Okay? Now, an, again, this is on page 59 in your notes. We've got the equation for an. It's 2 divided by t, the integral between minus t upon 2 of the function f of t times by cos 2n pi t divided by big T dt. Okay, so this is what we've got to try and find, an. Because bn we know is 0 because the function's even. Is there a constant term with that function? What's the average value of that function? Is it 0? No, so there must be a constant term. So what we'll do is we'll find the constant term first, then we don't need to worry about it later on. So A naught we have the equation for A naught. It's simply the same, starts the same way, minus t upon 2 of the function f of t dt. Now, because it's an even function, okay, well, let's first off stick that. We know that the period here is 2, so we've got minus 1 plus 1 f of t dt. This is A naught. Okay, and because this is an even function, we can say that this is equal to 2 times the integral between 0 and 1 of f of t dt. Because obviously it's even. The area on one side of the y-axis is the same as the area on the other side of the y-axis, so you can basically say that it's 2 times the area on one side only. And often when you've got a 0 in the integrals, it makes life easier because often the function will just be 0. Sorry? Which t? This t? Okay. That one? That one? Well, t is 2. If you look up here, this function here, it's got a period of 2. So capital T is 2, and so 2 over 2 is obviously 1. That's why it disappears. And here we end up with a t over 2, which is 1/2, or 1/2 of 2, which is 1. And then obviously we've got minus t upon 2, so you get minus 1 there. But like I said, because this is an even function, you can do 2 times one side of it and you get the same response. And so if we stick in we have t squared dt, and obviously the integral of t squared is 2 t cubed upon 3. between 0 and 1. And if you do the sums, you stick in 1, you get 1/3 times by 2. So that's 2/3. And obviously 0 as a 0 over 3 times by 2 is obviously 0. So this comes out to be 2/3. A0 is 2/3. So our constant term in this equation, the f of t, A0 divided by 2 is 1/3. Right, has everybody got that? Can I take it away? Yell if you've not finished it. Okay. Okay, so now we need to find the terms for AN. Okay, and AN, T over T. So we know that t equals 2, okay, and f of t is t squared. So we can put that in here, minus 1, 1, t squared cosine of, obviously that cancels with that, so we end up with cosine of pi n t dt. And obviously it's even function, so we've got 2 between 0 and 1 of t squared cosine of pi n t dt. Okay? How do we solve that integral? How do we solve that integral? Come on. First year maths, I think. Sorry? Integration by parts. How many times do we have to do integration by parts? Twice, indeed. So you should all be experts on this, but let's go through it anyway. Let's share the pain. So if we say that this is u, this bit's dv, we know that integration by parts is uv minus the integral of v du. And so the first step, we have 2 times, well, if u is t squared, du is going to be 2t dt. And we know that dv is going to be cosine n pi t dt. So v must be, what is v? Sine of n pi t divided by n pi. Yeah? Does everybody agree? So the first term, u times v, well u is t squared times by v sine of n pi t divided by n pi between 0 and 1. Minus the integral of v du. So the integral of between 0 and 1 of v du. So it's 2t sine of n pi t divided by n pi dt. And that whole thing is multiplied by 2. What sine of pi t? Well, sorry, what sine of pi n pi? Because obviously if you stick 1 in for t, you've got sine of n pi. What sine of 1 pi? 0. What sine of 2 pi? 0. Okay. So for any value in here, and obviously sine of 0 is 0, so that whole thing disappears. Yeah? So that whole term disappears, so we end up with this term here. What I'm going to do is I'm going to take the 2 over n pi out, and it's a minus sign, so minus 4 over n pi times by the integral 0 to 1 of t sine n pi t dt. That means we don't have to do integration by parts again. If I say this is u and this lot is dv, u equals t, so du is going to be dt, and dv is sine n pi t, v is going to be minus cosine n pi t divided by n pi. So plug it in, uv minus integral of du, so uv, that's going to be t times by v, so that's minus t cos n pi t divided by n pi. So we're actually just doing this integral. We've ignored the... Oh no, sorry, we have stuck it up there. Let's put that out here. So we have a minus 4 over n pi out here, okay, between 0 and 1, minus the integral between 0 and 1 of v du. So minus cosine n pi t over n pi dt. What larks? So, let's look at this term first. Minus 4 divided by n pi. Okay, this obviously becomes a plus because we can take the minus 1 out. 1 over n pi. Then we've got the integral of cosine n pi t, well that's going to be sine n pi t divided by n pi. Between 0 and 1. Look what we've got again. What's sine of pi? What sine of pi? If we stick in t as 1, what's sine of n pi? 0 again, so this term again disappears. So we end up with, this obviously minus comes out, becomes a plus, so that's 4. N pi times n pi is n squared pi squared. We end up with a 4 cosine of n pi. So what does this equal? Well, cosine n pi equals minus 1 when n is 1, 3, 5, 7 and so on. And cosine of n pi is plus 1 when n is 2, 4, 6, 8 and so on. Does everybody agree? And so basically this cosine n pi term makes this positive or negative depending on the value for n. Okay? So it's either minus 4 over n squared pi squared or positive 4 over n squared pi squared. And so we can stick this back into our solution for f of t. I'll write out the basic solution and then we can match it to this problem. Bn is 0. So if we plug in the values that we've got, we know that a naught over 2 is 1/3 plus the sum from n equals 1 to infinity of 4 over n squared pi squared cosine of n pi times by cosine of n pi t. So that's our value for the forcing function. And so I could even write this out in long, plus, oops, 1 over 3, plus 4 over pi squared, that's a constant, so that can multiply by the whole lot. We have, when n is 1, we've got cosine of pi, which is minus 1, so we have minus cosine of pi t. When n is 2, we've got cosine of 2 pi, so that's plus 1, so we have plus 1 over, we've got the n squared, so that's 4 cosine of 2 pi t minus 1/9 cosine of 3 pi t, and so on. And so what we need to do is we need to solve our differential equation, mx double dot plus kx equal ft for this term, the constant, for this term, the first one, for that term, the second one, and the third one, and so on. And then we add them all up together to get the total solution for x of t. So does everybody follow where we've got this f of t from? Yeah, everybody understands where this comes from. First year maths or second year maths, I can't remember now. Fourier series? So, there's our forcing function. Let's find the displacement. So that's a matter of solving this equation. So for the constant term, we have to assume xpi. So we're going to solve for, let's solve for this constant term first. So the constant term xpi is gamma. And so from that we know that x double dot pi is going to be 0. So we plug that into this equation, m times 0 plus k times gamma equals our constant term, 1/3. So from that gamma must be 1 over 3k. Yeah? And so xpi must be 1 over 3k. Okay. We have x of 0. Okay, this is x0. Now what about values for n equals 1, 2, 3, dot, 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 dot? We know that it's going to be a sinusoidal function, so xpi we try our sinusoid trial function. Okay, so that's our trial function. I'm going to make one quick substitution though. We know that t equals 2, yeah? So omega is going to be 2 pi divided by 2 equals pi. And the other substitution I'm making is if we say that n omega is omega n, okay, so that's the other substitution I'm making. So we can replace n pi with omega n. So that's what I'm going to do. xpi just makes it easier to write. Cosine, and makes it more recognisable as well. So x dot pi, we have minus omega n alpha sine plus omega n beta cosine. X double dot pi minus omega n squared alpha cosine of omega n t minus omega n squared beta sine omega n t. So that equals minus omega n squared times by x pi. So we plug that into our equation of motion. We have m minus omega n squared alpha cosine Okay, so that's my differential equation with this substituted in, okay, becomes a lot more complicated, equals an cosine of m pi t, which is what we've got up there, I think, somewhere. There's an cosine m pi t, okay. That's an, that's cosine m pi t. And so obviously we can rewrite this in terms of alphas and betas to get the alpha and beta terms out. So let's look at the alpha terms. Alpha must equal minus m omega n squared plus k equal an, because that's all the cosine terms connected together. Because we've got minus m omega n squared times by alpha cosine omega nt plus k alpha cosine omega nt equals an cosine omega nt. Cosine omega nt disappears, okay? We end up with that equation to find alpha, okay? So from that equation we can see that alpha is an divided by k minus m omega n squared. For the beta terms we have a minus m omega n squared plus k equals 0. The only way that's possible is if beta is 0. We're almost there. We're almost there. So for xpi, for when n equals 1, 2, 3 and so on, we have alpha times cosine of n pi t. So that's an divided by k minus m omega n squared cosine of omega n t. So x of t, we have to do with a constant term, or we found x of t with a constant term, that's 1 over 3k, plus for n equals 1 to infinity, we have our xpi term, an over k minus m omega n squared cosine omega nt. Well, obviously we can stick in our value for an in here. So 1 over 3k plus over pi squared Well, obviously I can replace that with omega n. Yes? You can stick the, in fact, the solution, which option here. Okay, basically that n pi, which we've determined right at the top, is equal to omega n. So I've just stuck that in there. The other, well, obviously this term and this term could be combined and you'll have omega n squared there as well instead of the pi squared. It's up to you. So, if your forcing function happened to be a series of parabolas, okay, t squared, then that would be your solution. Okay? So just to recap, the process to go through is you need to find a solution to the Fourier to the forcing function, that being the Fourier series in this case. Okay? You then go through and you solve for x for every value of n that you've got. So n equals 0, you've got a constant term, you need to find x of 0. And then for n equals 1, 2, 3 and so on, you need to find another value for x where n is 1, 2 and 3. x1, 2, x2, x3 and so on. And then at the end you just add them all up. X of 0 plus x of 1 plus x of 2 plus x of 3 and so on. You just add them up and you get your solution for x of t. So if we go back over the problem that we've just done, we've got our function, okay, that's been defined over here, and we go through and we find the Fourier series. There's the general equation, and we go through and we find the Fourier series. We've got a of 0, and we find the Fourier series is here, okay, or there, it's up to you. We've got a value for a of n. So there's our Fourier series, and what we need to do is we say, okay, well let's look at what happens when n equals 0. Well, if n equals 0, we can forget about all of that because that's n equals 1 to infinity. So that goes, we solve for x of 0, which is just the constant term. So we did that and we found that x of 0 was 1 over 3k. Okay, so we can bank that. When n equals 0, that's the value for x. Okay? We now need to solve for when n equals 1, or n equals 2, or n equals 3, and so on. And so we can take this equation, that equation, and we can solve for x for when we've got that equation. Now, that looks complicated, but I know that this bit of the equation is a of n, so I'm going to just stick a of n in there. Okay? We can substitute back later on. So we're solving for a of n cosine of n pi t. Okay? A of n cosine of n pi t. That we know is a simple sinusoid. Okay, we're solving for a of n cosine n pi t. Okay? If you went back to your chapter 3 notes, we solve for f naught cosine of omega t or whatever. Okay? It's the same thing. Okay, except for this time a of n is some function that we'll worry about later on. Now because we're solving for a sinusoid, we try a trial function which is a sinusoid. Okay, and you go through solving the same way that we did for chapter 3. X pi, x double dot pi. You solve it into the equation, and that equals our forcing function, a of n cosine n pi t. When n equals 1, 2, 3 and so on, that's our forcing function. Okay? So we go through and solve for alpha and beta, which are the unknowns in this equation. We get alpha as a of n upon k minus m omega n squared. And then we can plug it all back in. X of t is our solution for when n is 0. 1 over 3k. And then we have a sum term, because we've got 1 to infinity, n equals 1 to infinity of a of n. This lot here, an over k minus m omega n squared cosine omega nt. Okay? And if we substitute in our value for a of n, you end up with this lot. And simplified, with making the right substitutions, we end up with this as our solution. Okay? So that's following the steps. You find your Fourier series of the forcing function. Okay? You then solve for each value of n. Here I solve for n equals 0, and I solve for n equals 1 to infinity in one group. And then you solve for x of t by just plugging everything back in, adding up all those values, x of n's, okay, plus x of 0, you add them all together, you get the total solution. Okay.